Hello, everyone. Welcome to System and Skill 2021 Summer Edition. My name is Yun, an engineering director in Facebook, and I will be your host for this event. Like everyone else, I have been working from home or living at work, as someone may say, for more than 1 year now. Even though I really enjoy spending time with my family, looking at my kids' arts all the time, I still miss the face-to-face interaction with friends, co-workers, people in the community. Fortunately, we figured out a way to engage with people virtually. This is the third time we run the System and Skill event online. Thank you very much for the strong participation. Given the optimistic trend of a pandemic control, we might be able to hold the next event in a less virtual way so people have deeper engagement. Starting from today and for the next 3 weeks, we will have a session of technical talks following by a panel discussion/Q&A every Wednesday. Today, our session will be focused on reliability and overload resilience. First, we'll hear from David Yanacek from AWS to talk about avoid overload in distributed systems. Please welcome David.
Hello, everyone. Thank you for joining today. I'm here in Seattle in a conference room in an actual Amazon office building. Have our foosball table here behind me. I'm really excited to win some games once we start getting back together. But we're here today to talk about some techniques that Amazon uses to build systems that avoid overload. So we'll talk through some techniques and examples of how we actually do it a little bit under the hood. My name is David Yanacek, and I'm a senior principal engineer here at AWS. I've been here for about 15 years at Amazon, but I'm currently working on AWS Lambda. So I'm going to be using some examples of how we built Lambda under the hood in order to give some examples of just how we build these systems. So avoiding overload is a pretty big topic. It kind of ranges from operational approaches on how to react to it to architectures that can avoid it kind of entirely and intrinsically. So we'll cover these two areas. We'll talk about load shedding and what the goals are of load shedding, and then we'll talk about how queue-based systems are particularly susceptible to overload because they kind of build up a lot of traffic even after the overload subsides. So just to start, let's talk about what I mean by overload. And so for this, I'll go back to when I was in high school and kind of early in college. When I was learning the code, and when I was learning the code, I kind of learn about kind of algorithms, and I would see the world around me, and I'd think, oh, actually, kind of what I'm seeing around me is kind of like an algorithm just playing itself out in the real world. And so one place I saw this happen is when I worked at a bank. I was kind of in high school and a little bit in college. I was a teller. And the tellers, you go into the bank, they will do transactions, do deposits, withdrawals, and that sort of thing. And I was really at this bank that I was seeing kind of algorithms play out. So one thing you can do at a bank is you can drive up in your car and just send your transaction through this pneumatic tube. And so air kind of pushes it underneath the ground or over the top. And then I get the transaction. I'll do some stuff, send it back, maybe for somebody to sign something, go a little bit of back and forth. And so at the bank, there are actually multiple pneumatic tubes. So a bunch of people can be doing transactions in parallel. And while I'm waiting for one to complete, I can kind of multiplex and work on the other transaction. But unfortunately, sometimes I would take on too much work all at once and I'd become slow. So it felt like my throughput was good. I was getting a lot of transactions done, but each of the transactions was taking longer because they'd be waiting on me instead of me waiting on them. And so one time, actually, I was so slow that a customer got so kind of frustrated. They were had such a deadline to get somewhere else, and they didn't want to sit there. So they actually asked for the transaction back through the tube and left because they had to go. And so that wasn't great. That made me feel bad. I didn't like letting them down. So what this kind of comes down to is in terms of algorithms and systems, is something called Amdahl's law, or the universal scalability law. And what it essentially says is that you can parallelize a system up to the point until contention becomes the bottleneck, and then it kind of you can't get any more throughput out of that system. And so what this kind of looks like in terms of a computer system is you have say a server somewhere that's pictured on the right with some CPU, there's some disk capacity and I/O throughput that it can do, some network throughput that it can do. So on the left is this graph on the x-axis is throughput. And as throughput increases, you see the y-axis latency of the system also starts to creep up a little bit, because at the beginning where the system is idle, there was all of the resources were available to those first couple of requests that were happening. But as throughput goes up, each following request has fewer and fewer incremental resources on the server in order to process the request. And so things start to slow down. And eventually things slow down so much that the system is doing a whole lot of work, but not getting anything done in time. And so one thing that happens, especially if the fastest request gets so slower than a client timeout, like if a client is making a remote call to your server and it'll time out and stop waiting. If your fastest response time is slower than your client timeout, then that means your server is doing a lot of work and accomplishing nothing useful. It's running at 100% utilization, but no client requests are being actually handled in time. So that's unfortunate. Another way to look at this effect is if you plot throughput on the x-axis and something called goodput on the y-axis. So we'll define goodput as the throughput that the requests that are handled in time and without errors. And so you can see that there's actually kind of a plateau. Typically, ideally, this would go up and to the right forever. It would be an infinitely scalable system. Magically and infinitely scalable forever. But of course, at any instant in time, a system only has so much compute resources available to it. And so there is a maximum. But the problem here is that if it gets slower and slower, goodput actually drops off and actually starts accomplishing nothing useful. So that's not good. The problem here is that servers are too optimistic. They'll just keep giving whatever requests we hand at them, they just keep working on them. And that's not good. And what this means is when the system is overloaded, it's given too much work to be able to handle, it actually starts wasting work. And the last thing you want to do when you're kind of approaching overload is waste work. Everything is even more precious at that point. Making matters even worse, as I mentioned, clients will time out. Well, one thing that clients often do is retry. And so what that means is when a client does get a timeout, it might retry that request, resulting in even more wasted work, and it'll drive kind of the system into overload even deeper and faster. Now, one thing that the AWS SDKs do when you call an AWS service is they will retry for you, but they have this circuit breaker built in so that if the retries aren't succeeding, if the client is observing too many errors from that particular service that they're talking to, it'll stop retrying. It'll still try. It'll do the initial request. It's not a circuit breaker that will create errors or anything. It'll actually, it's a circuit breaker that just stops retrying because it notices that the retries aren't helping, and so it stops those. It's a pretty nice trick. That's a technique that you can read more about in different blog posts or just use in your own. You can use that technique in your own kind of client-server interactions. The way to avoid this situation is load shedding, and load shedding is all about cheaply rejecting excess work. The idea is simple. Once a server reaches the point where it's starting to slow down, if it's handed a request at a higher rate beyond that, it rejects those excess requests. And that results in the latency of the requests that it does serve as being nice and uniform. Now, there are a lot of heuristics that you can use, that we use to determine what that breaking point is for a server. Maybe if the CPU utilization is high, that's a good indicator that it shouldn't take on more requests. Or if a client is above a quota, or if the latency is increasing, or if the current connections in the system are high or too high. You can find all these different signals in order to decide when to reject requests. Now, of course, this is load shedding. Load shedding is a last resort. Of course, systems at Amazon, what's important for everybody to do is to forecast what the load will be, to make sure that we're scaled ahead of time and to react. So if there is a system that needs to be scaled reactively, that happens automatically without humans in the loop. So that's important, and that's very important. But I'm kind of talking about that other extreme where, well, what if there just weren't enough in place at that instant in time? And so the idea is to keep this curve of goodput. The goodput should just plateau until we can add more capacity as far to the right as possible to handle as much offered load and ignoring that excess offered load, but still maintaining that goodput. And of course, it does drop off eventually. Eventually, a server is given too much. It's too expensive even to drop those requests. But we need to make sure to have it so that the system can handle as many as possible and reject excess requests as cheaply as possible. And so these things it's important to do load testing. I know there's another talk at this conference about load testing later. And so take a look at that, because it's important to do that and see what the little things are that can be more expensive than you think. Like it could be that the server is accidentally logging stack traces when rejecting a request. That could be a big problem. That could be even more expensive than just handling the request in the first place. So look for those modalities. So at Amazon, we use a lot of layers in order to kind of protect from to make it so that the server can reject so much. Maybe the kernel helps with IP tables, and beyond that, a load balancer can help. And so it's just, we try to let the server be in control of knowing what its capacity and utilization are, but it enlists the help of layers of like an onion of protection to be able, then the objective is to push this curve of good put out as far as possible. Now, having to think about and rebuilding all of these layers of load shedding, whenever we build a new system at Amazon, it made us think about whether we were missing an abstraction to make this a little simpler for developers building systems. And so one such abstraction at Amazon is AWS Lambda. With Lambda, Lambda is what I work on, I mentioned it, instead of provisioning kind of compute resources explicitly, customers upload their code, and then we handle spinning up and down compute resources to run your code as just in time as needed. So when you kind of think like ultra reactive auto scaling. So we'll spin things up in like tens or hundreds of milliseconds right as those compute resources are needed. And so that's Lambda. Now, the resources that Lambda spins up are called execution environments. And each execution environment comes with a configured fixed amount of CPU, memory, networking, disk, that sort of thing. And now the key is that those are fixed for each invocation, not just each function, not just for your piece of code, but it's fixed for each invocation of your function. So every time a request comes in, Lambda spins up a new execution environment just for that invocation to use for that moment. And so if another concurrent request comes in for your function, we spin up another execution environment. Now, if one request finishes and another request comes in soon after that, we'll still leave that execution environment around to use for another request in the future. But the key is that each execution environment is working on only one request at a time. And so what that means in terms of like load shedding is that as throughput increases on the system, each request has the same amount of resources available to it as the previous. And so what that means is latency doesn't go up just from the Lambda compute capacity. Latency stays flat. So it's just a thing that a system builder doesn't need to then worry about. Of course, your application could be talking to a database or something like that. It doesn't just magically remove this as a problem, but it simplifies it, because now this layer of compute, at least, is going to behave predictably, even at load. So to recap what load shedding is all about, the idea is just to cheaply reject excess load. Of course, auto scale, make sure to be prepared for any spikes in load. But when the inevitable happens and there is a spike in load, make sure that the system doesn't fall over and collapse. It should still achieve everything that the capacity can do. And then there are some systems and approaches that you can use or build to change the game and simplify it for people, like giving each request its own sandbox. In fact, actually, one thing we call these execution environments in Lambda is a sandbox just internally, and that internal name, means that we can have fun toys like little sandboxes with Lambdas in them. So anyway, it's just a random aside there. But let's keep moving on to chapter 2 then. So the next thing I'd like to talk about here is a trickier version of overload, and that's for queue-based systems. Sometimes we think that queue-based systems have it easier because, if we get too many requests, we'll just queue them up. But unfortunately, that isn't always what the customers of that system want. And so let's just look through a fake example here. Let's imagine that there is a system that is a chat application where, let's say, Alice and Bob can use this system to talk to each other or whomever else. And so the system looks like this. Alice might send a message to the group, and then that would be handled by some web service layer. Maybe for kind of retry, to make sure that we have durability and to make sure we send it to everybody, we want to enqueue that message somewhere so we don't lose it if there's an error during processing. So we'll put it into some durable queue. In this case, we're using Amazon SQS. And then we'll have a different system pull messages off of that queue and say archive the messages so that if people rejoin, they can see the chat history. And then we'll query a different table to see who all should receive a copy of the message and then send it out through that kind of, say, a WebSocket or something like that. Great. Okay, so let's zoom in on that kind of queue because that's where things can get a little crazy. So let's say, typically there's no queue backlog or a very small one because the system is operating, well within its kind of capacity. Well, what if there's suddenly a lot of people suddenly want to start talking about something. Well, now there would be a whole lot of messages. The system scales up reactively. Database kind of heats up, all this stuff. So maybe there are too many messages for it to be able to handle, but that's okay. They're all just being queued. Well, the problem is, let's say the load subsides, there's still a ton of messages in the queue to work through. There's a big backlog that remains and needs to be drained with even more capacity maybe behind the scenes. So we've made it really hard to recover in a system that uses a queue. So what's the ideal customer experience? Let's work backwards from that. Well, let's think about what's not ideal. And this is a classic Byzantine generals problem where Alice might agree with Bob to meet at a certain time using this messaging system. Bob says, okay, I'll see you at 3 o'clock. Alice tries to reschedule the meeting at the last minute, but this queue is backed up for other reasons. And now Bob goes to the meeting and is sad. So this is not ideal. The problem here is that queue backlogs are really getting in the way here. It creates a modal behavior where you have this mode where the queue is empty, where things work one way and have certain performance characteristics. And then you have another mode where the queue is backed up and the system is just a completely different thing. So the problem is sometimes queues that we use like this, these durable queues, have a FIFO-ish behavior. Messages, not necessarily FIFO guarantee, but they generally behave in a FIFO-ish kind of way, where the producer is putting messages at the front of the queue, but the consumer is consuming the oldest message always from the queue. And so when there is a backlog, it slows every message down. Every message the consumer pulls is the oldest. That might make this kind of chat application difficult. Now, if we were to instead use a last in, first out queue, a LIFO queue, producer and consumer would be both working on the newest messages. And so if there were a backlog, it would only delay the messages that arrived during that load, when the backlog was being formed. And that might be a better property of a system like this chat system. So how can we take these queues that exist that are kind of FIFO-ish, but make them behave LIFO-ish? And we can do that by using multiple queues. So maybe this chat system could have 2 queues that it uses behind the scenes, a high priority one that it favors, and then the low priority one that it would use only when it has time. So you check here first for messages and check in the low priority queue when there's nothing else to do. And so we'd be putting messages into the high priority queue all the time. And so let's say there's that surge of messages, queue fills up a bit. So the chat service, well, eventually those messages have been in the queue for a while and they start to become kind of these older messages. So that's why they turn green. Well, when the new messages might come in that are fresher that we'd rather be working on. So when the chat service is processing these messages, it could receive one and then just, oh, this is an old message, I'll put it into the low priority queue. And then if it sees a high priority message, it'll just process that right away. And eventually it moves it works through that backlog. This assumes that moving a message is far cheaper than actually processing it. And that can be a fairly fair assumption. You have to do that load testing to make sure that is actually valid. But moving the message means that the backlog is cleared out faster and we're back to processing the real-time messages, and then we can get back to the ones that were being sent before during that load spike. So great. Now, another approach that you can use is just to avoid that infinite backlog in the first place. A queue can be good for some amount of buffering, but maybe we don't even want to drive a backlog. And so a technique we use at Amazon that you all can use is called rate limiting or throttling to apply back pressure. So if there's no nominal load, just normal load coming in, the queue, things are behaving fine. But if there is a spike, some kind of like an API server can do rate limiting and just reject that excess load. And that way, I mean, in some ways with this chat application, that would have been favorable because then Alice would see, oh, Bob is definitely not going to get my message right now. The app is giving me an error. I'm going to go call Bob or send Bob a text message or something like that. So let's talk about one kind of last technique that we use at Amazon to kind of avoid this type of thing altogether in a multi-tenant system, where there are multiple people using Lambda all at the same time. And so let's go under the hood into Lambda, into one facet of Lambda called the async path, the asynchronous path. So there are 2 ways you can invoke a Lambda function. You can invoke and call the invoke API and say, hey, run the function, here's the input for the code, just give me the output of the function right away, synchronously in the same HTTP reply. Then there's asynchronous, where you can say, hey, Lambda, run this function. I'm not going to wait around for it to finish, but run it. And you can set policy to say if your function crashes in the middle of it, you can move it into a dead letter queue, retry it. There's other kinds of configuration there. So that's the asynchronous style. And so here, when you invoke a function, you call the invoke async API. There's a load balancer This is pretty familiar looking probably. There's a fleet of servers we call the front-end service that does kind of all kinds of validation, authentication, authorization, rate limiting, etc. The front end is queuing that message into an SQS queue. And then we have a different service called the poller that's grabbing messages from that queue and going around and invoking the API for the customer, just the normal path. So that's pretty much, and then when we confirm that the function has executed fully, we delete the message from the queue. So otherwise, we'd move it into a different queue or something like that, a dead letter queue that you configure. Okay, let's zoom in on these components that we really need to focus on for the queue backlogs here. And so here there are, Lambda is a multi-tenant service. There are many of you out there using Lambda. And so each of you are maybe denoted by a different shape and color here. And so typically there are some messages from everybody in this queue. Great, no problem. But what happens if one of you gets really excited and starts using Lambda a lot? Well, now that could drive one of these backlogs where this same queue is, like the poller is having to sift through all of these messages, and it's like, there is a backlog. It's okay for a customer to have a backlog, but we want to make sure it doesn't affect all the other customers and introduce latency. So one thing we could do is we could just create a bunch of queues, like a whole lot. One for every customer. And that would work. It would mean that if the star customer were to drive a backlog, it would only affect them again. Okay, fine. But this is not what we do. It's because if we were to do this, we would have to be pulling a huge number of queues constantly just to see if any of you happened to invoke your function at that instant in time. And so this would be expensive and wasteful. And so what we do instead is a technique called shuffle-sharding. And in shuffle-sharding, we create a fixed number of queues. And we map everybody to k queues, let's say 2 in this example. And so when we put a message into the system, we first check to see which of those 2 queues for that customer is the emptier, and then we put the message into the emptier of those 2 queues. And so let's say that star customer drives a backlog again. Well, now you would think, okay, this is going to affect other customers, but actually, because we check to see which queue of the 2 for that other customer is emptier, we route around it automatically. And so it may seem, okay, there are still some overlaps. If you looked at that picture, it might not quite be ideal. But actually, there's some kind of magical math going on, some mathematical kind of statistical properties at play here that make this pretty impressively good at just isolating workloads. So let's say you have 8 queues and you map everybody to 2. Well, the probability of you completely overlapping with, say, a noisy customer, a particular noisy customer, is 3.6%. And so that's not great. That's a pretty high percentage. But if you tweak the numbers a little bit and have 100 queues, it's still a manageable number of queues, and you map everybody to 5, well, now there's just such a small percent chance of somebody completely overlapping with a hot customer, for example. And behind the scenes now, so we do the shuffle sharding, and then behind the scenes, we are noticing when a customer is driving a backlog, and we move them into their own queue at that point in time, because then there's no reason not to. Just to recap on avoiding backlogs, we want to make sure that when we build systems that use queues, that we don't accidentally introduce a modal behavior where a backlog can make customers unhappy. And we can apply back pressure as sort of a last resort to keep that as one technique. We can use multiple queues. Priority queuing is another technique. Or we can use a technique called shuffle sharding that we described here. And you can use reshuffle sharding actually for request reply services too that are doing kind of real-time stuff, not in queuing. We do that a bit as well. And it has these magical properties of isolation that are pretty nice. So just to recap everything, avoiding overload is all about not taking on too much work. We want to make sure good put stays flat by rejecting the excess work. We want good put to remain as constant and so that we don't just collapse. We also can change the game a little bit using a service like AWS Lambda to make it so every request has the same amount of work than the previous. So these overload situations don't really happen. And then we can isolate backlogs using techniques like shuffle sharding to make it so that the traffic that is needing to be shed is isolated from others. Now, we barely kind of scratched the surface on these. You may actually have we probably debate some of these techniques because there's a lot of nuance here. And so we've actually written a lot more detail about these topics and published it in the Amazon Builders Library. So if you want to read a longer article about any one of these topics that I talked about, like shuffle sharding, check out the Amazon Builders Library. So thank you, everybody, for coming.